Okay, I hope everyone can hear me. I'm sorry that we're a little bit late getting started. I usually get onto Blackboard, a half hour before our class session is supposed to start, and today it wouldn't let me in, and then once I got in, I couldn't do anything. So it's been kind of frustrating, but hopefully everything will be working okay. My microphone was acting a little strange too in Blackboard. Can you hear me okay? Okay, good. All right, well, welcome back. I hope you all had a great spring break and that you got to do something fun over the break. We don't have that much left in the course. We're into week 9, and the actual course materials only go through week 13, and then 14 will be prepping for the final exam. So it's even though we're kind of just past the halfway point, I think it's going to go pretty quickly. Before I get started, did anybody have any questions on anything? Okay, well this week we're going to talk about mass storage, but before we get into the actual lecture for this week, I would like to go over a couple of the homework assignments that we didn't have the opportunity to go over because of the midterm and because of spring break. So the first thing I want to go over is your week 6 exercises. And some of you did very well on the first part of this, but then some of the other parts you were a little confused, so I'd like to go through it a little bit with you. You were supposed to convert the virtual addresses to the equivalent physical addresses and give the answers either in hexadecimal or decimal. It was actually easiest to do this in hexadecimal. Converting it to decimal and doing it in decimal actually is a lot harder, because all you really had to do in this exercise was to take a look at the addresses and look at this first number here, this hexadecimal number, and look that number up in the table that you were given. So in E is a 14, so I would look that up in the table. That would be my page number. Then I would look for the frame number that was next to it, which was a 3, and I would simply replace that 14 with a 3 in my hexadecimal address. Okay, and that's all you needed to do to convert the addresses, is just take the first digit, look it up in the table, and then replace it. Okay, so that was what you had to do with each one of these. The other thing that you needed to note, though, that most of you did not realize as you were doing this, remember what the page frame table is doing is it's helping keep track of what pages are in memory, what frames are being used, so that when it's time to replace a page, it uses this to look up to see if a page is in memory already or needs to be replaced. And a lot of you missed this part of the question. Set the reference bit for the appropriate entry in the page table. Okay, so in your page table, when a page is referenced in memory, the reference bit gets set, and that's what I did here, so that the operating system would know what page was least recently used or used more recently or whatever, depending on the algorithm that you're looking at. So that was another part of the question. Most of you didn't turn this table in, and that was fine. It didn't say to turn it in. But you needed that information when you went on to the next part of the question. Any questions on this part? Okay. So it says, using the above addresses as a guide, provide an example of a logical address in hexadecimal that results in a page fault. Okay, so a page fault would happen for any page for which the page frame is not in memory. In this case, it would be any logical address that starts with 4, 8, C, or D. Okay, so here we can see that the pages here that where there is no page frame, these are the pages that aren't in memory. So that's where I got this part of the answer, saying that any logical address that starts with a 4, an 8, a 12, or a 13, which is C and D in hexadecimal, would cause a page fault. Okay, so I just gave an example of hexadecimal C171 would cause a page fault. Any questions on that? Okay, now here's the part that most people had problems with, where it was asking what set of page frames will the LRU page replacement algorithm choose in resolving a page fault. So the answer here is any page frame where the reference bit is 0 would be a candidate for replacement because we set the reference bit to 1 when the page was used. So if we want to do the least recently used, we have to look for ones that have not been used recently, and those would be any of the ones where the reference bit is 0. The other thing that people got confused with is it asked for what is the set of page frames. So it's looking for not the pages, but the page frame numbers. So in this case, anything where the reference bit is 0 would give me page frame 9, 1, 14, 13, 8, 0, 4, or 2. And that was the answer for that one. Any questions on that? Okay. So your next exercise was discuss the situations in which the MFU, most frequently used page replacement algorithm, generates fewer page faults than the LRU page replacement algorithm. Also discuss under what circumstances the opposite holds. So here I was looking for 2 different examples, and the way I answered this question was to actually come up with some page reference strings in which MFU would generate fewer page faults, and then another one in which LRU would generate fewer page faults. So here's an example where MFU has fewer page faults. Here's my page reference string, 1, 2, 3, 4, 4, 4, 5, 1, and I just filled out this table the way we did in class, looking at both the MFU and the LRU algorithm. So what would happen here is MFU would generate 5 page faults, and LRU in this sequence would generate 6. Now the problem is that even though I came up with an example that worked, chances are this example would probably not happen very often in real life, because usually what happens is a page that was recently used usually gets used again, okay, in the near future. Okay, usually when you're accessing pages, especially when you're looking at a program, an application, it's usually accessing pages, you're executing the code kind of from the beginning to the end, and so it usually doesn't have to jump back to an earlier page, like I did in this example where I'm jumping back to page 1, which was already taken out of memory. Okay, so this is one example, and you could have come up with any example for it. But usually LRU is a better algorithm. And here, this next example this, let me see, I labeled this page wrong. This next example, and I'll fix this before I send the slides out to you, is an example where LRU has fewer page faults than MFU. So it's LRU has fewer page faults than MFU. It's actually pretty hard to write with a mouse here. So, but I'll fix the slide before I send it to you. Okay, so here was just another example, and this is a more realistic example of how this will work. And I'll get to your question in a minute, Hala. Here, we're accessing 1, 2, 3, 4, 4, 4, 5, and 4. And here, MFU causes more page faults, causes 6, where LRU causes only 5. And that's a more realistic example, because chances are if we were working on page 5 in memory, it's more likely that the next thing you access would be on page 4 rather than going back to page 1. Okay, so that's all this problem was talking about. Hala said, depending on what you determine the number of rows. Yes, this would change depending on the number of pages that you can have in memory. So your example could be very different than mine if you only used 3 or if you used 5. And it's kind of like the programming problem that you're doing right now. You can choose how many pages are going to be stored in memory, and usually in an operating system you would configure it to hold a certain number of pages. And so that's really something that gets configured in the operating system, and you could tweak it and change it in order to help how quickly pages, how many page faults are happening and so forth, if you have access to that type of thing in your operating system. Okay, we don't have that kind of access usually, if we're working on a Windows or an Apple computer, but on some mainframes or larger computer systems, you may be able to tell it, here's how many pages I want you to be able to store in memory. And you can kind of prevent your system from having to page things in and out from memory very often. So that's sometimes configurable on an operating system, Hala. And so, in this example, it just said to show an example, and you could have used however many pages in memory as you wanted. Does that answer your question? Okay. Okay. So so that was the answer for that exercise for week 6. Now week 7, you had a few exercises as well, and in week 7, the first question is asking if the operating system knew that a certain application was going to access the file in a sequential manner, how could it exploit this information to improve performance? Now remember, when you're accessing things in a sequential manner, you're accessing, one block after the other from the file. And so if an application is going to access the file sequentially, you can improve performance by reading in multiple blocks when you're doing a read operation. Okay, rather than reading a block and reading another block and reading another block, because as you'll look at this week in your reading, it takes time for the head to be positioned and then to read it as the disk is rotating. So what you would want to do for efficiency is read in, a number of blocks into a buffer in memory, and then just when you actually perform the read operation or the next read operation in your application, it would really just be reading it from memory and not from disk. So that's the kind of answer that I was looking for in this question. Are there any questions on that, on what a sequential file is, or why performance would be improved by doing a prefetch of the blocks? Okay, well, let's move on then to the next question, which was, give an example of an application that could benefit from the operating system support for random access to an index file. And here, remember that with random access, you're not reading a file from the beginning to the end. Okay, you're kind of reading it, wherever the data is. In other words, you might have, in my example here, I said, any application that uses an identifier or a key to access the records could benefit from application support for an index file. Okay, you have a question. Is it possible in sequential access to read multiple blocks at a time? Yes, the operating system would be able to do that. And actually, depending on your language, if you're working in a very low-level language like assembler language, you could actually tell it how many blocks that you wanted the operating system to read in at a time. But usually, if a file is tagged as a sequential access file, and you can do that in most programming languages, it will read in multiple blocks, assuming that you're going to want to access this file, kind of reading it from the beginning to the end. Okay? Does that answer your question, Hala? Okay, when you say the blocks that are read must be sequential, like 1, 2, 3, there are you talking about the relative block number, or are you talking about the physical block number? Remember that your blocks really can be anywhere on disk. So it may be actually, physical block number, 47 on the physical disk, but you will be reading them in order from the lower numbered blocks to the higher number blocks. So that's what sequential access is. It's always those particular blocks in order from the beginning of the file to the end. Okay. Okay, to go back to the indexed file, the kind of answer I was looking for here is that any application that uses an identifier or a key to access the records could possibly benefit from application support for indexed files, or actually operating system support for indexed files. Records accessed in a banking application, for example, would not be accessed sequentially. You wouldn't necessarily read a file of accounts from beginning to end unless you were doing something to every single bank account in the file. Usually, somebody wants to deposit to their account or withdraw from their account, so it depends on that particular customer's account number what blocks you want to read into memory. So in a banking application, the application might use an account number as an identifier in the record, and you wouldn't necessarily be accessing the file in a predetermined order like we just talked about with sequential access. An index file would be more efficient because the index could be searched to find the records in random order rather than having to read the file from beginning to end every time in order to find a particular block. Okay? Any questions on that? On the random access and why indexing might be better? Okay. Now this question, the next question asked, if you have a file system on disk that has, assume you have a file system on disk that has both logical and physical blocks with sizes of 512 bytes. Assume that the information about each Okay, can you hear me now? Okay, for some reason I got bumped off of Blackboard Collaborate and I had to get back in, so sorry about that. I was just about to talk about contiguous allocation. The first part of the question is, how do you convert from the logical address to the physical address? And so with contiguous allocation, what you would do is divide the logical address by the block size of 512. The quotient will be the block number. Oh, I'm sorry. Okay, I'll go back one. The previous slide was just going over the question. Okay, so we're going to be doing question 11.7, where we're looking at a file system that has logical and physical blocks of 512. And it's asking first, how is the logical to physical mapping done? And then second, how many blocks must be read in order to read block 4 from disk? Okay? So we're here looking at contiguous allocation. And the way contiguous allocation works is when you have the logical address, you have to divide the logical address by the block size of 512. And that will give you the quotient, which is the block number, relative to the beginning of the file. The remainder is the displacement or the offset. And you had a homework problem way back when where you worked on a little program actually to do this. So what we're looking at here is remainder being the displacement of the offset, and then the physical block number is equal to the starting block number plus the relative block number. So in the directory here, you can see there's a starting block number. So you would, calculate the relative block number, add it to the starting block number, and that would give you the block on disk. And so with contiguous allocation, you can get direct access of a block because you just look it up in the directory. And remember, it said assume that the information about the file was already in memory, so we don't have to worry about reading the directory into memory. And so all you would need to do if you were the operating system is look up the starting block number for the file, add the displacement to that, and you would be able to read that block directly. So only one block would need to be read to get to block 4 if you have contiguous allocation, because you just look up the starting physical block number, you add the relative block number to that, and you would get the physical block number. Okay, any questions on contiguous allocation? Okay, moving on to linked. Now, linked allocation is a little different because if you remember with linked allocation, every block not only has your data in it, but it also has a pointer to the next block. It's like a linked list on disk. So the answer that you would give here would depend on how long you assume a pointer is, how many bytes a pointer is, because the pointer will take up a certain number of bytes in a block. So I just gave a general answer here, and you may have given one more specific if you made a certain assumption about the number of bytes it took to store a pointer. But your block size would be something less than 512, or the amount of data you can store in a block would be something less than 512, because there would also need to be a pointer stored in each block. So if P is the size of the pointer, then each block would contain 512 minus P bytes of data. So to get the physical address, you would divide the logical address by 512 minus P to get a quotient and a remainder. Okay, the quotient indicates how many blocks would have to be read in the linked list, and the remainder would be the offset into the block. Okay? So what you're actually doing is you would look up the starting block number, and then you would get the relative block number from the beginning of the file, and that would tell you how many you had to read. So if your quotient was 0, it would mean you would only read one block, because block 9 would be the first block, and that was the block that you wanted to read. If you had more than, if you wanted to read something other than block 9, you would have to then traverse through your linked list looking for the correct block number. Okay? So now, then assuming your block numbers start with 0, and again, some people actually assume that it started with 1, and I'll accept it either way, but assuming the block number started with 0, 5 blocks would need to be read to get to block 4, because you'd have to do block 0, block 1, block 2, block 3, and block 4 to get to the relative block in the file. Okay? So all we have here is the starting block. We don't really know what the actual block number is for these. Here you can see our actual block numbers are things like 16 and 1 and 10, because we're not calculating the actual block number. We're just saying how many blocks from the beginning of the file do I have to traverse my linked list to find the actual block I'm looking for. Okay? Any questions on that? Okay. So let's go on to indexed. And indexed, again, we're going to be dividing the logical address by the block size, which again is 512 now because we don't have these pointers anymore. You get a quotient and a remainder. The quotient is the index, and the remainder is the displacement or the offset. What you would do is you'd have to first look up the index block, read that block into memory, because that's going to tell you where all the other blocks are for that file. So what you would do is you would use that quotient when you did the division to look up that number in the table, which is your index, and then you would go to whatever physical block it pointed to in memory. So if your quotient was 0, it would take you to block 9. If your quotient was 1, it would take you to block 16. If your quotient was 2, it would take you to block 1, and so forth. So you're just using this logical address to find the index into your index block, your index table here, and then you're just doing a direct read from the proper position in the file. So how many blocks need to be read depends on whether the index block is still in memory. Because of course the only thing you have in your directory, which is in memory, is the address of the index block. So you would have to, if the index block is not already in memory, you'd have to read that in first and then read the block that you want. If the index block is already in memory, it would only take one block read, because you wouldn't have to read the index block, you'd just have to look up the correct block in that index block. Any questions on that? Okay, so that brings us to this week's new topics, which is the mass storage. So we're going to be looking at the physical structure of secondary storage devices, explain the performance characteristics of mass storage devices, evaluate the disk scheduling algorithms, and then discuss the operating system services provided for mass storage, or RAID and arrays and that type of thing. So those are the different topics that are covered in your book. Okay, so the important thing for you to understand is what a hard drive actually looks like on the inside. And what a hard drive looks like is you have multiple platters, which are just flat disks that have a magnetic surface on it, and there are more than one of these in a hard drive, and those are all on what is called a spindle, and they spin around at a very high rate of speed, and on this magnetic surface on each of the platters, information is written and read. The concentric circles on the platter are called tracks, and the tracks are made up of sectors, and then your blocks are mapped to the sectors in a file. Okay, so this thing is spinning around very fast, and this ARM assembly with our different read-write heads, which are these are your heads here, that's moving in and out very, very rapidly as it's looking for these different cylinders on disk. And so a cylinder is really just the same track on every platter of this disk. So if this was track 0, and this was track 0, and this was track 0, and no matter how many platters you had, all the track 0s would be a cylinder. Okay, because the arms are fixed. They all move in and out at the same time. And so when it moves something to track 0 on one of the platters, it moves it to track 0 on all of the platters. And so that's really called cylinder 0 because it's all those tracks all the way down on your hard drive. The disk drives rotate very quickly, 60 to 250 times a second, and they can even be faster than that. You have your transfer rate, which is how fast data flow between the drive and the computer. And then you have some other times, like your positioning time, and so that's the time it takes to move this disk arm to the correct cylinder. Okay, that's your seek time, plus the time it takes for this platter to rotate around so that the correct sector is under the read-write head, and the read-write head is just right here at the end of each of these arms. Okay, so you have to kind of imagine this disk spinning and these read-write heads going in and out, on these platters, and then as it's spinning very quickly, it has to know when it's positioned over the right sector in order to read the logical blocks. And we just talked about, some of how you do the addressing to get to the correct logical block. Now the thing is that's very interesting. I actually used to work in a factory where they manufactured hard drives, and I actually wrote software for the robots because we had robots actually manufacturing these disk drives, and the disk drives had to be manufactured in what was called a clean room setting. In other words, when I wanted to go in and actually touch any of the equipment that we had in there or do anything on the computers in there, I actually had to get dressed from head to toe in like a gown and a hood, and I had a mask, and I had to put little booties over my shoes because we could not have any dust in this environment, because these heads are flying over these platters so quickly, and they're so close to the platter that a particle of dust would cause what's called a head crash. Okay, and I have a cool graphic here on what this would look like enlarged many, many times. So if this is your read-write head, and this is your platter with the magnetic surface on it, there's this little tiny gap in between your read-write head and the actual platter. And that's so small. It says here like 3 nanometers. And to just give you some perspective, if that's the size of the gap, this is the size of a smoke particle. This is the size of a fingerprint. this is the size of a dust particle, and here's how big a human hair would be. Okay, so that's how close that read-write head is flying over these disks. So anyway, I just thought that was cool. We use hard drives mostly for our long-term storage and to store lots of data, but there are other types of secondary storage. Okay, Hala, you said it should be protected. Yeah, that's why, exactly, your hard drives are in a sealed case. But I was talking about the case where, you know, we were actually manufacturing the hard drive. So we were manufacturing the platters themselves and putting the substrate on it, putting the magnetic coating on it before it was even built into a hard drive. And then, you know, everything in this factory was done by robots, not by humans. Because until we got into that sealed case, you had the chance of getting some dirt or dust on these platters. Yeah, it is pretty amazing. I thought it was cool. It was a really fun job too to actually be programming the robots to do this. But anyway, that's a whole other story. So to get back to our lecture here, we're going to be talking mostly about hard drives, but just be aware there are other types of secondary storage. One would be a solid-state disk where you don't have these platters and these arms and doing the reading and writing. You could use non-volatile memory to act like a hard drive, and it's more reliable, faster, and consumes less power than a hard drive. But the problem is that, at least at this time, it has less capacity usually, a shorter lifespan, and it's more expensive than a magnetic hard drive. So you know, you might be using these in some of your devices, but usually you have a hard drive that you're using. Another form of storage that you hardly ever see anymore is a magnetic tape. But usually if you ever watch an old movie or an old Star Trek episode or, you know, those type of things, you always would see these big reels of tape moving back and forth. And these are kind of like cassette tapes, if any of you remember. I know at least one of you in the class is as old as I am, so you remember cassette tapes. But some of you may not have ever seen a cassette tape, but you might remember a VHS tape. Those are all magnetic tapes. And in the old days, everything used to be backed up onto magnetic tape. And so they were these big spools of tape, and it was just thin. And Hala asked if it's used for backup now. It is in certain cases, but usually more likely what's used for backup is just another hard drive, possibly a removable hard drive. Some places still use tape for backup, but it is very rare now, because if you look at this magnetic tape, you know, if your tape breaks, which could happen fairly easily, it's just this very thin tape covered with a magnetic surface, you know, pretty much you've lost a bunch of data on your tape. So people don't use tape so much anymore. They usually use a removable hard drive, and on like mainframe systems, it's actually this whole sealed pack that you actually stick into a hard drive unit and can back things up to, and then you pull it off and can put another hard drive in there. Or you may use other things for backup. Some people use flash. Some people use, you know, a hard drive that's connected, an external hard drive connected to your computer. So magnetic tape really isn't used as much as it used to be. But we're going to be talking mostly about disk. And so one of the important things with disk is you want to minimize the amount of time it takes for it to read anything from disk. And so you want to kind of optimize how it's reading these blocks from disk. And this is what we're going to be looking at in our homework assignment as well. So the operating system is responsible for using the hardware efficiently. You want to minimize the amount of seek time, in other words, the time it takes for the disk arm to move the heads to the correct cylinder, and then the amount of time it takes for the disk to actually spin so that the sector is under the disk head. And then you also want to minimize the bandwidth, and maximize, the amount of bandwidth. And the bandwidth is the number of bytes that can be transferred divided by the total time it takes to do the first request for service and the completion of the last transfer. So it's transferring all the bytes from your disk. So access time and bandwidth, which you want to kind of improve, you could improve it by managing the order in which the disk I/O requests are serviced. Because if you're servicing things and you're not doing a lot of moving of the heads so that you're able to read these bytes in very, very quickly, because you're not moving the head in between the reads, then your performance is going to improve. So the first scheduling algorithm that we're going to look at is first come, first serve. Now here, you can imagine this kind of being your platter on disk, and these are your cylinder numbers going from 0 to 199. So your data is on these different cylinders on your disk, and the queue is just first come, first serve order. So you request data from cylinder 98, followed by cylinder 183, followed by cylinder 37, 124, 14, 24, 65, and 67. So with a first come, first serve algorithm, and your book assumes that your read-write head is starting here at cylinder 53, that just happens to be where it's positioned at the time, and it's moving, in this case, let's assume it's moving out toward 199, so it's moving kind of from the lower numbered cylinder out to the higher numbered cylinder. What it would do is have to move from 53 to 98, then out to 183, then back to 37, then out to 122, then back to 14. And so if you're imagining those read-write heads, they're going in and out and in and out and in and out on this disk, because your read-write heads, you can kind of think of kind of flying over this surface if we're imagining this as being the surface of the disk. So they're going in and out and in and out, kind of in this pattern that you see on this chart. Okay, so yeah, it'll take a long time, relatively, to access all these different cylinders. And you could calculate how far the disk head is moving, and that's what I've done here, and this is what you need to do in your homework. So with a first come, first serve, we're assuming that our head is positioned at cylinder 53, then it has to move out to 98. So I can calculate how far it goes to move from 53 to 98 by simply subtracting 53 from 98, and I get 45. So it had to move 45 cylinders to do that one positioning. My next one is position 183, and so I'm at 98. I have to move from 98 to 183. Again, I just do the subtraction, and it's calculating, it's not blocks, remember here, Hala. It's calculating the distance between the cylinders is what it's calculating, okay? Because remember, what we're doing here is we're not looking at the blocks now, we're looking at the cylinders. Okay, and that's exactly what you're doing. You're calculating the distance. And so then it went from 183 to 37. So again, to calculate that, I just subtract 37 from 183 and so forth. And I do that for each one. I go from 37 to 122, 122 to 14, 14 to 124, and then 124 to 65, then 65 to 67. And I just do that calculation, the simple subtraction for each one. I add it all up and find that it's moved a distance of 640 cylinders using first come, first served. Okay, any questions on that? So you're asked the same kind of question in your homework. You're given a bunch of cylinders in the queue, and so you just have to calculate from where the disk head starts to the last cylinder in the queue. All right. Another algorithm that you're going to look at is the shortest seek time first. So again, our queue still looks exactly the same. The queue doesn't change. What changes is the algorithm that's used to determine where the disk drive head should move next. So here what we want to do is start at 53 again, but now what we're going to do is look at all the numbers in the queue and say which one is the closest to 53. Because that's going to be the shortest distance, the shortest seek time. So we're going to go from 53 to 65 would be the closest. Okay, and then from 65, the next closest to 65 now, I went from 53 to 65. Now the next closest is going to 67, which is very close. And then we have to look at what's the next one. Well, our candidates here would be either 98 or 37. 98 is 31 positions away, but 37 is the next closest. It's only 30 positions, so the head would move back out to position 97. I'm sorry, 37. And then we have to decide what's the next closest, and here the next closest would be 14, so it would move back again to 14. And then we have to look at what's left and say, what's the next closest? And the next closest now is 98, so it's going to move all the way back to 98. And then it will move to 122, and then to 124, and then to 183. So it's just looking at from where I am right now, what is the next closest cylinder that's being requested? And again, you can go through the same kind of calculation. We went from, we're not going now in the order of the queue. That was first come, first served. Now we're going in shortest seek time. So I'm starting at 53. I look at my queue, and my next closest number is 65. So I calculate the distance between 53 and 65, and I get 12. Then I say the next closest one is 67, so I calculate between 65 and 67, and I get 2. Then I went to 37, so I calculate the difference between 67 and 37, and I get 30. And then I look at what the next one is. The next closest is 14, so 37 minus 14 is 23, and so forth. And I do that for all of till I've looked for all of the cylinders in the queue, and I add up all those numbers, and I can see now the distance that my head has traveled is only 236. So it's a big difference going from 640 down to 236. Okay? So that's one of the other algorithms that you're going to have to do in your homework assignment. We also have scan. Oh, before I go on, were there any questions on shortest seek time first? Okay. Now, oh, Hala, did you have a question? Okay, that one's easy. Okay, great. So then scan is a little different. Think about an elevator, and they call this one the elevator algorithm, because think about how an elevator goes up and down from the floors. Let's say it starts, you're at floor 12 and you want to go to the top of the building. It goes up and it stops at each floor along the way. And then when you're at the top, it starts going back down, and it stops wherever it needs to along the way. And it just keeps going back up and back down all day long. And that's kind of how the scan algorithm works. and you have to know which direction it's moving. So in the example in your book, it shows that it's at 53, but it's moving towards 0. So now we're going to start at 53 and say, what is the next one that's closest to 53, but moving in the position toward the lower numbers? Okay, so now we're going to go from 53 to 37. So even though 65 was closer, your book in this example said, let's assume that the arm is already moving toward 0. So you want to keep it moving in that direction. So we go from 53 to 37, then it's still moving in the same direction, and we would hit 14 would be the next cylinder, and then we keep going until we finally get to the one end of the platter, and then we have to move in the other direction. So it starts moving in the other direction, and we would, the next cylinder we would hit would be 65, then 67, and then it would go out to 98, and then it would go out to 122, 124, 183, and if we continued on, it would go out to 199. And when it hit that, it would start going back. Now you have to assume while these things are happening, more cylinders are getting put into the queue that need to be read because, you're always reading and writing to your hard drive. So this thing would just kind of keep going now. It would continue back and read any cylinders that it needed to, and then it would go back in the other direction, and it would just keep doing that all day long. Okay? So once we know what cylinders it's going to access in what order, we just go through the same algorithm. So here we went from 53 to 37, and we calculate that, and so on and so forth. And when I calculated this all out, I added this up, and I came up with 236, which was actually the same as it was with our shortest seek time first. Okay, it won't always work out that way, but in this example, it just happened to. Are there any questions on scan? Now I know we're at the end of our time, so if you have to leave, you just can leave. Don't apologize or anything, just leave. I'm going to keep talking, and you can go to the recording when the recording's available, and just pick up where you left off. Okay, so if you need to leave, I totally understand, and just drop out. Okay, so that was scan. So you could think of that one like an elevator going from 0 to whatever the highest cylinder number is on your disk and back again. Okay. Now C-scan takes it in a slightly, it's kind of like scan, but it does it a little bit differently. If we go back to the scan, okay, where we were going, back and forth, when it hits the end of the disk here, end of the platter, it actually there was a pretty long way that it had to go to before it would get to another cylinder that had to read, because we already read all the cylinders going in this direction, so we need to just kind of start again, a little past where we started from before and start reading in the other direction. So the C-scan kind of says, well, instead of doing that, why not just go, since most of your cylinders now are going to be on the other side of the platter, when you get to one end, why not just go to the other end and start reading again? Okay, and again, your drives can be going either from from the low numbers to the high numbers, or from the high numbers to the low numbers when it's doing the scan. And in this example in your book, they decided to go from the low numbers to the high numbers when this scan is starting, when this algorithm is starting. So here we want to start at 53, and now we're going to 65, 67, and so forth. And we're going to just keep going to the higher numbers until we finally hit the end of the disk, and then we're going to just hurry up and go all the way back, because the arm can move faster if it's not reading, because it's not waiting for anything to happen, it's not waiting for the disc to spin. It'll simply move all the way back to the beginning and then start looking for cylinders again. And remember, new cylinders, cylinders to be read can be all along here, because they keep getting added on our platter, or maybe I should show it up here. They could be added at any time while it's already reading other cylinders on the disk. Okay, is the direction important in C-scan? It's important in any of these, just as you're doing this particular calculation. Okay, you have to know which direction it's going in first. In order to do the scan. But in the overall scheme of things, whether you're starting at the high numbers and going to the low, or the low to the high, with any of these algorithms, it's not going to make much of a difference, assuming that your data is evenly distributed all over your disk platters. Does that make sense, Fatima? I mean, it's important that you know that when you're trying to calculate how far it's moving. But in the overall scheme of things, it's going to just be going back and forth, back and forth, back and forth all the time. Okay? So we just need to know what direction it was in as we started, when so that we know how to do the calculations. So when we do the C-scan again, you just need to know what order that you need to figure out what order the cylinders will be accessed. And so here we went from 53 to 65, and we can calculate how far that was, then from 65 to 67, and so forth, all the way until we get to 183, which is the highest number in our queue, but then we still have to calculate how far it went to get to 199, which was the highest number cylinder on our platter. And then we have to calculate to go all the way from 199 back to 0. Okay, and I'm just going to flip back here a second. So we went all the way to the end, and then we need to go all the way back to the beginning. Okay, so when we go through these calculations, you just calculate all these distances, and then you add it all up. And in this case, I came up with a number of 382. Now, when you're doing your homework assignment, I'm asking that you show your calculations. Show me so I can see where you thought the head was moving and you know how you calculated this. So if your answer is wrong, if you just told me, you know, if you came up with an answer of 247, I wouldn't know how you got that answer, and so I'd have to mark the whole problem wrong. So what I want you to do is tell me how you came up with it, kind of like I did here, saying what cylinders it would move to, so that I can see kind of how you came up with your calculation. Okay, Hala has a question, and the question that usually jumps to her head: who is responsible for determining the algorithm? The operating system program, or it depends on the type of the disk, and why can't you use the best algorithm all the time? Okay. The answer to that is it depends. the algorithm to actually move the heads and whatever really depends on how the physical drive is being presented with the cylinder numbers. Okay, so here's the cue that the operating system is working with. But the operating system will use an algorithm to then tell it to, you know, actually access the cylinders in this order, the order that we determined here. Okay, so a lot of times that's done in the operating system. On rare occasions, sometimes there's smarts, intelligence software in the different controllers for the drives and whatever, but usually it's done in the operating system. And so the operating system programmer would determine it, or it would possibly depend. You may be able to configure your operating system to use a different algorithm. And why can't you use the best algorithm all the time? Well, it really depends. It depends on, as it depends on what data is being accessed. Just think back to even our bank account example that I talked about before. It's going to be accessing, maybe you have 1 million customers at your bank. You don't know how it's going to be accessing the data and where the data is placed on the disk, so that how can I say this? You're going to be jumping all over in this data from one data item to another, and so it's not fixed the way that the data is accessed. Every application, remember that we're talking about the operating system. So if you have a big mainframe computer, every application is accessing the disk, and different applications are accessing different files, and different files use different cylinders, and so these heads are moving in and out all the time. So what you try to do is figure out, if you know how your system will usually be used, because you might have a system that's used in banking, and you kind of know what applications are running on your system, you may be able to figure out a good algorithm to use, but sometimes you can't. And so, and we'll be talking about this later, but actually, shortest seek time first is often a good algorithm, even though some of them will perform better in some cases. A lot of systems default to shortest seek time first because in a lot of cases that gives you good performance, even though it might not be the optimal performance. Okay? So it's kind of hard to tell what the best algorithm is going to be because you don't know how your computer's being used all the time. And when you do know that, you can kind of guess, but you don't always know for sure whether you're using the best algorithm, you as an operating system developer or as someone who's tuning the operating system. Okay? Does that answer your question, Hala? All right. Okay. So the next algorithm that it talks about in your book is look, but it doesn't actually give you a chart for look. So I kind of created one saying, here's what's going to happen with the look algorithm. The look algorithm is like the scan algorithm, so it starts, going in the direction that the disk head is already moving, but it doesn't go all the way out to the end. Look is this red line here. I just took the chart for scan and I added this red line because look says if I look ahead and I don't see anything between where I am currently and the end of the disk, if there are no reads that have to happen or writes that have to happen, I might as well turn around now and start moving in the other direction. And that's what look does. Okay, so in this case it would go from 53 down to 37, then to 14, and there's nothing between 14 and 0, so it would turn around and start going in the other direction and then go to 65, 66, and so on until it got to 183. Now there's probably more things to read after this. This is just a snapshot of what's in the queue. So if 183 was the highest number, it would turn around immediately and start going in the other direction once it hit 183. It wouldn't go all the way out to go between 183 and 199. So look is very similar to scan, except you don't have those little extra movements to get to the actual end of the platter. So here's what look would look like, and this is a scan with look ahead. Again, we start at 53, we'd go down to 37 and so on until we got to 14. But now we don't go from 14 all the way down to 0. We go from 14 up to 65 and continue in that direction until we get all the way to 183. And again, you're just going to do the calculations, and you can see here I came up with a number of 208. So it was actually better than my scan algorithm because I'm not doing those little extras at the ends of the platters if I don't need to. I'm not doing that little bit of extra movement at the ends of the platters. And then finally, we have CLOOK, which is like CScan, but it does look ahead. So again, here I'm assuming, your book assumes for some reason, in this case again, it's going from the low numbers to the high numbers. They keep flip-flopping in the examples just to show you that, your heads are going to be moving in and out all the time. And so we don't really know what direction, and so we can calculate it just depending on which direction the head's moving. So here you're moving from the inner cylinders, or the lower numbered cylinders, to the outer or higher numbered cylinders. And so again, it's doing like a scan, but now it does the look ahead. It doesn't go all the way out to 199, and that's the look part of it. But then the circular part of it is, rather than start scanning in the other direction or start looking for cylinders in the other direction, is going to go all the way back to the lowest number cylinder and then start reading from there. Okay? So again, it doesn't do that little extra between 0 and 14 and 183 and 199 in this case, because it doesn't need to. Okay? And that's the look ahead feature. But then the circular feature of it, the C part of it, the circular feature of it, just means that it doesn't read anything on the way back. It simply goes all the way back to the lowest number cylinder and starts again. So again, we can do the calculations for this. Again, we go out all the way until we get out to 183. When we get to 183, we don't go all the way back in. We want to go just back to cylinder 14, and then continue our scan in that direction, in the opposite direction. So if I add all these up again, now I came up with 322. And I'm not 100% sure I did all my math correctly, but I think you get the idea. And again, that's why I want you to show your work when you do the problems, so that I can see, if it was just a simple math mistake, I won't take credit off for that. So just show me your work. Okay, and this was something that Hala was asking before, is how do you choose? Okay, shortest seek time first is the most common, and they're definitely better, just about anything's better than first come, first served. But scan and C-scan perform better for systems that have a heavy load on the disk, because it doesn't have to do all these calculations for each cylinder that it's looking for. It's just going to keep moving in and out and in and out and in and out. And the other problem with shortest seek time is, remember that there is a possibility, if everything's kind of clustered in the middle of the disk, there's a possibility that some of your cylinders will never get accessed, because if a new cylinder needs to be accessed and that cylinder is close to the cylinder you just read, starvation could occur. You might never get to those cylinders that are out near the edges of the disk, because you keep going back and forth every time there's a new cylinder. If it's near the middle tracks of the disk, you may never get to those. So that's one of the reasons why scan or C-scan might be used rather than shortest seek time first, because you don't want to have starvation. You want to make sure that you get to those outer cylinders at least once in a while. And again, like I was telling Hala before, performance depends on the number and the types of request. It also depends on how your files are allocated, where your directories are, where your index blocks are. I mean, it's very complicated to determine what would be the right disk scheduling algorithm. What's usually done is, and this again goes back to what I was talking to Hala about, is that it is in the operating system. A lot of times you can configure it or put in different algorithms. In some systems it's done usually on mainframes where someone can actually tell it, okay, if the operating system has these 5 algorithms that it can use, which one does some human think that should be used? Or the operating system can determine which algorithm can be used. Sometimes just as operating systems are developed, new algorithms that are more efficient might be developed, and then they would just be, when you did an operating system upgrade, it would automatically replace what algorithm is being used. Okay? So shortest seek time first or look is a good choice if you don't know what to choose. And another thing to realize is with solid state drives, there is no disk head movement. So most solid state drives, the operating system will just use a first come, first serve algorithm because you don't have these heads moving in and out. It's just like accessing memory. It just accesses the location with the solid state drive. So this gets us to our homework question. And this is, suppose that a drive has 5,000 cylinders. They're numbered from 0 to 4,999. The drive is currently serving a request at cylinder 2,150, but the previous request was at 1805. This tells you that the heads are moving from the lower number cylinder to the higher numbered cylinder. Okay, Hala, you said this is like the new type of hard disk, the SSD. Yes, yes, that was that picture I showed you of, by the magnetic tape. It was a solid state drive, and so that's one where we're not actually having the platters, and that's faster and more efficient, but again, it's more expensive, and those are usually smaller. You can hold less data at this point in time. Now, if you were taking this operating systems class 5 years from now, I might have totally different answers to these questions. But you're correct, Hala, that the solid-state drives are the new type of disk drive that are used in a lot of devices rather than the old magnetic drives, although old magnetic drives are everywhere. And so this is still an important topic at this time. So to get back to the homework assignment, sorry for that little diversion, but realize that it already read cylinder 1805, it's now read 2550, and now you want to determine how is it going to read these cylinders depending on the algorithm. Okay, so you want to assume that it's starting at 2150 and it just came from 1805, so you know it's moving from the lower number to the higher numbers. And then you want to just calculate that distance for all the different algorithms. So the same thing I did on the previous charts for the example in your book, you want to just do those calculations for this particular queue of cylinder requests. So assume this is your cylinder request. You're currently at 2150. You're moving from the lower numbers to the higher numbers. And then how do each of these algorithms work? Okay, just the calculation, or should you draw? Somebody had asked me that, and I actually posted it out on the discussion board. Just do the calculation. Just show the calculation, because sometimes you might have just subtracted wrong and you'd come up with the wrong answer even though, or you added wrong and you might come up with the wrong answer even though you actually understand the concept. And so by seeing your calculations, I'll see that you understand the concept and I can give you credit for it even if your final answer is wrong. Okay? So show your calculation. You won't get full credit if you don't show your calculations, but I will give you partial credit if you have an incorrect answer as long as you show your calculations. And if your answer is just a simple addition and subtraction problem, like it wasn't actually a misunderstanding of how the algorithm works, you know, if it's a simple addition or subtraction problem, I'll give you full credit for the calculation. Because I could see that you understood how each of these algorithms worked. So that's why it's good to show your work. Okay, I'm going to continue, and again, if you have to leave, I'm perfectly fine with that. Just drop out as you need to. A few other topics I'm just going to go through quickly is understand how disks are formatted. There's a physical formatting that happens on your disk. This is when your disk gets divided into the sectors, and each sector contains data plus other information used by the disk controller, the sector numbers, the error correction, and so forth. And so that's usually done kind of at the factory. The low-level physical formatting is done. Every once in a while, you may have to reformat your hard drive, especially if you're starting to have errors on it. You may end up backing all your data off your hard drive, having to reformat it, and then reinstall your operating system and everything else because some sectors went bad. But usually, the formatting is done at the factory. And this error correcting code, that's how, some of your computers, you may, every month or whatever, it might be doing a scan of your hard drive, and it'll give you some error message that your scan failed, and it means that some sector has gone bad on your disk. It figures that out because it uses an error correcting code that is actually a calculation as it's scanning your disk, as it's reading your disk. It actually keeps kind of a checksum that'll tell it whether it read all the bits the same way the bits were written out. And so if bits are lost or corrupted, then it can detect that. Okay? And you might see those errors sometimes when your disk is being scanned. So the operating system is what partitions the disk into cylinders. Then there's logical formatting, and that's where you create the file system, which is your mapping of the free and allocated space and the directory structure, the initial directory structure. That's your logical formatting. And then remember, this is even something that you had to review for your midterm, is that the raw disk, rather than a cooked disk, is unformatted. So that certain sections of the disk may be left unformatted, and that won't use the file system. So if you're reading something from raw disk, that means there's no buffer cache, no file locking, no prefetching, no space allocation, no file names, no directory services. All these things that we've been talking about these past couple weeks don't exist when you have a raw disk. The raw disk is usually used for applications that want to do their own block management, but usually we're using the logically formatted part of the disk. All right. Related to this is different things about disk blocks. Your book talks about boot blocks and how your system actually boots. There's a small bootstrap program that's in ROM, in read-only memory. Then the full bootstrap program is stored in boot blocks at a certain location on your disk, and that's how your operating system gets loaded. So your bootstrap loader is stored in your boot partition, and then once that's read, that will read everything else it needs in order to get the rest of the operating system up and running. And you kind of see this sometimes when you're rebooting your system, that there will be some messages about what it's doing as it's actually loading in the operating system. Okay, because disk drives are so fragile, there is this thin magnetic coating on the drives, and it could get corrupted, and it can just start failing. The magnet part of it kind of wears off, or if you have a very powerful magnet that you put by a hard drive, that will corrupt your data, might make some of your blocks go bad. And so the system often keeps track of this. Defective sectors and bad blocks are flagged so they won't be used. On some systems, there's something called sector sparing, where some of your sectors aren't written to. They're only used when a sector goes bad, and so the operating system will say, oh, you wanted sector 42? Well, 42 went bad, so I put the data in 57 instead. And that's kind of what sector sparing is. 57 was a spare sector, where it would move data if a sector was going bad. And then there's also sector slipping, where it actually will shift the sectors on your disk when one goes bad. So the operating system takes care of a lot of these things. It's also, you also might see this if your disk is fragmented. That's kind of like sector slipping. When you defrag your disk, what it will do is start copying things off and shifting things around so that you got rid of all that external fragmentation. Sector slipping is kind of like that, where it's moving everything, but it's really, instead of moving it to eliminate fragmentation, it's moving it in order to move things away from bad sectors. All right. Swapping. We talked about swapping a few weeks ago, where you're moving processes between disk and memory. A lot of people talk about swapping now as virtual memory techniques to swap pages, not just entire processes. And so your swapping might be in your file system. Remember, it's paging in and paging out. It might be part of the file system, which would be easy to implement, but it's not very efficient. Or it may be in a raw partition. The operating system might be doing the swapping outside of the file system because that's faster. Modern operating systems only swap out pages that aren't already in disk, and they also can be optimized by only allocating swap space on the disk when a page is being forced out of memory. Okay, so if you remember back, we talked about swapping, and your book goes into more detail on, now that you know more about how disk drives actually work, what that means to swapping. And then finally, the last part of your book talks about RAID, and this is a fairly new technology, which is a redundant array of independent disks, and where you have multiple disk drives all storing the same data. And what we're trying to do with RAID is improve both reliability and performance. So RAID improves reliability because you have data stored on multiple drives, and you can also store some extra information so that if one of the hard drives, if there's a failure on one of the hard drives, you can rebuild the data that was lost because you store this extra information on a different drive. RAID also talks about mirroring, where every disk that you have is duplicated, and whenever you write data to disk, you're actually writing it onto two disks, so that if one fails, the other one still has the data, and it would actually do a failover, start just using the drive that still works. Okay, but you could imagine this is more inefficient because you're actually writing to two drives all the time. But in some cases where the data is extremely important, RAID is used quite a bit. And then your book talks about some of the things you look at when you're talking about reliability and performance. And one is mean time to failure. What is the time on average before a disk will fail? Mean time to repair. How much time does it take to replace a disk and restore any data that used to be on the disk before it failed? And then mean time to data loss. How much time is it where you're not able to store any data or read any data, or data gets lost? So your disk drive might be failing, and it might originally just detect that one sector went bad. If you could very quickly bring another disk drive up and running on your system and move all your data over to that drive, then you won't lose very much data, even if more sectors go bad on the drive that's starting to fail. So that's what RAID does. It gives you these extra disk drives so you can move very quickly onto another drive if you need to. It also improves performance because now you have these multiple drives, and information can be read from more than one disk at the same time. It can increase the throughput because your different pages that you're reading in can be on different drives, and so you're not always waiting for the rotational, for the disk drive to position its head and wait for the rotational latency, wait for the disk to spin to position itself correctly, because you might be doing one read on one drive and the next read on a different drive, and so there's not the wait time. Things are happening in parallel. RAID also improves performance by storing redundant data, and I talked about mirroring or shadowing, which was the RAID 1. They call it on in your book. There's different levels of RAID, and then RAID 0 and 1 is mirroring, but they're striped. And it talks about disk striping in your book. In disk striping, it uses a group of disks as if it's one storage unit. And so you can even do bit level striping, so that if you had 8 hard drives, for example, and you say write out a byte, it would actually write out a bit on drive 1, drive 2, drive 3, drive 4, drive 5, drive 6, drive 7, and drive 8. To write that whole byte out, it would actually spread 1 byte over 8 disks. Okay? And so all those disks can actually be writing all at the exact same time. So that's how you get improved performance. Okay, and it talks about you're able to stripe bits, you're able to stripe blocks, you're able to stripe sectors. I mean, there's lots of different ways that you can use these parallel disks. And then with block interleaved parity, which is RAID 4, 5, and 6, there you have a lot less redundancy. You're not writing the data in multiple places. So your book talks about in great detail about RAID, which is a fairly new technology. Okay. So that's kind of the high points of what's in your book. Of course, your book has more detail on all this. Any questions on anything we covered today? I'm sorry that it went so long, but because we went over the homework assignments and we had 2 of them to go over because of spring break and whatever, and the midterm, it took a little extra time. Any questions? Okay, well, thank you so much for being patient while I had my problems with Blackboard, and thank you for coming. And as soon as I get off here and the recording becomes available, I will be sending these slides out to you. Okay?